evening. I'm Spot On Weather meteorologist Matthew Euler. Welcome to my video training series again, my next video that I plan to throw in the training video series. And tonight we're going to talk about temperature controls. So let's go ahead and get to this. All right, so the overview on temperature controls. Let's take a look. There's many factors that cause changes in temperature across the Earth. Now, temperature across the globe, whether we're talking about warming and cooling, that temperature is going to result from the amount of solar energy reaching the Earth at any one point. Additionally, daylight hours and the intensity of incoming solar radiation are also important. What we're really going to focus in on in this training video is the main factors that really play a significant role in an area's temperature. And those would be latitude, the land-water distribution, the ocean currents, as well as the elevation. So let's first talk about latitude temperature controls. All right, so latitude and the tilts of the Earth play a big part in where our planet receives most of the solar energy. Now, latitude is just simply those lines that run east to west that are either north or south of the equator. If you're on a particular latitude line north of the equator, we call that north latitude. If you're on a particular latitude line south of the equator, we call that south latitude. Now, the tilt of the Earth, that basically means that the Earth is tilted at 23.5 degrees. So it's tilted on its axis as the Earth revolves around the sun. Now, the angle at which solar radiation strikes the Earth is about 90 degrees. The sun's incoming solar radiation is much more direct at the equator at 0 degrees latitude. This is going to result in much more intense solar radiation over a more concentrated area at the surface. At the poles, however, so we're really increasing the distance from the equator, the sun is low on the horizon, so we have a low sun angle, with the incoming solar radiation, which is going to be spread out over a much larger area. And I'll show you an example of that here in a moment. Now, the fact that solar energy is spread out over a larger area, that means there's going to be more atmosphere for that energy, that solar energy to pass through. And that's going to result, that greater distance or a greater amount of atmosphere is going to result in many things happening to the incoming solar energy, from scattering to reflection. In other words, it's going to result in cooler temperatures, even when the sun is above the horizon for 24 hours a day. And I do have a video coming up on the seasons. There is a period of time during the Northern Hemisphere summer in which, let's say, for example, the North Pole has 24 hours of daylight. And you would think with those 24 hours of daylight that those temperatures would be warm because the sun is always above the horizon. It never gets dark completely. And that is not simply the case because of how low the sun angle is and how much more atmosphere that solar energy has to pass through. And again, there's many things that can change the direction of the incoming solar radiation, such as the scattering off molecules, the reflection off molecules. There's albedo when you have snow-covered ground that reflects, up to 95% of the incoming solar radiation. So in general, those temperatures, despite having 24 hours a day in the polar areas, are still cold. All right, so this is a great example of what's going on when we talk about a temperature control and look at latitude specifically. All right, so we have the sun over here on the left, and each of these solid dark lines represents the direction of how that solar energy or solar radiation is hitting the various latitudes of the Earth. So we see we have 0 degrees latitude. This is where the equator is located. And then we have 30 degrees north latitude. We have 30 degrees south latitude in the southern hemisphere. We have 60 degrees north latitude in the northern hemisphere up here. And we have 60 degrees south latitude down here in the southern hemisphere. Now, whenever you see, I want you to compare the oval shapes here, okay? Now, based on the Earth and its tilt, right? Again, it's tilted at 23.5 or 23.5 degrees. It's tilted at that on its axis. axis, 23.5 degrees. Because of this, the most direct incoming solar radiation falls on the low latitudes, okay? Specifically at the equator here at 0 degrees latitude. But you notice this orange oval, okay? It's much smaller, right? Incoming solar radiation over a smaller area, more direct incoming rays, and that's going to result in greater heating per unit area at the surface, more direct and concentrated heating. Compared to this large yellow oval in the higher latitudes, okay, this solar radiation, look how large this oval is as compared to the orange one we just discussed. So you have the angle at which the sun strikes the Earth's surface at these latitudes is spread out over a much larger area. And that's going to result in more diffuse radiation, incoming solar radiation. It's going to result in colder temperatures as compared to this little orange oval where you have much more direct or more intense solar radiation at the lower latitudes. The next temperature control we'll talk about is what's known as land-water distribution. Now, just keep this in mind that land and water, they're both going to absorb and give up heat. But in general, land tends to warm and cool off much more readily as compared to water. A good example of this, to kind of put it in perspective, is when you walk barefoot on the beach on a hot day, right? It almost feels like the sand is so hot it's going to burn the bottom of your feet. It's almost too hot to stand on that sand. But then you put your feet in the water and it's much more bearable. And the water is cooler as compared to the very hot land, the hot sand in particular in this case. Now the pattern would reverse if you went back to the beach at night after sunset. The sand is actually going to feel cooler on your bare feet and the water is now going to be more comfortably warmer. So in general, the specific heat of land versus water is much different. Land is going to heat and cool 5 times faster than water. And if we just took a look at the soil properties on land, let's say you've had a lot of heavy rain and the soil is very wet or very moist. Moist soil is going to heat and cool about 3 times faster, all right? And that is in relation to that water again. So, we talk about excessive heat waves in the United States in summer. Well, when that soil is super dry, it tends to heat up much more effectively as compared to when the soil is moist. Additionally, when you talk about water, it has a property in which it retains heat energy much better than the land. And as a result, water, it can store large amounts of energy while undergoing only small temperature changes. The oceans basically act like these huge tanks of heat energy, and they modify the temperature significantly. So in general, because of this land-water distribution, if we talk specifically about an area that's on the coast near larger bodies of water, the winters usually tend to remain warmer and the summers cooler than inland regions away from the water. Next, let's talk about the ocean currents and how they control temperatures. So as the wind blows over the oceans, it's going to cause the surface water to move along with it. That energy is going to transfer from the wind to the atmosphere down to the ocean surface. This leads to further movement of water, extending further down in depth, several hundred feet deep. And along the edge of continents, we have these ocean currents, which influence air temperatures significantly. And I'll show you a map here in a moment of all the global ocean currents. In the northern hemisphere, in the middle latitudes, when we talk about middle latitudes, we're talking between 30 degrees and 60 degrees latitude. Adjacent to the east coast of continents, ocean currents transport warm water poleward. Meanwhile, on the west coast of continents, ocean currents transport colder water equatorward. So some coastal areas experience upwelling. That particularly occurs off the coast of California, where you get a wind that generally blows parallel to the coast and then it wraps clockwise around the eastern Pacific high pressure system and takes the top layer of water, the wind blows over that water, takes that top layer of water and takes it out further away from the California coast, and beneath that top layer of water that's being taken away from the California coast, you have colder water beneath that comes up to the surface, and this is known as upwelling, which can make water temperature is even cooler. Now, when the prevailing wind blows over a warmer or cooler water surface, the air temperature is impacted along coastal sections. And so I kind of added this, places like Central California, the San Francisco area, they're generally much cooler in the summer as compared to an East Coast location such as North Carolina, the coast of North Carolina. They're generally around the same latitude. You could literally draw a line from San Francisco straight across to North Carolina, and it's pretty much the same latitude, but because of the influence of ocean currents, that cooler ocean current, California current off San Francisco, it's much cooler there as compared to the coastal portions of North Carolina, because you have more of the warmer ocean current, the Gulf Stream current offshore. So if we get, like, for example, a westerly wind to blow over the cooler water into San Francisco Bay, the temperature is going to be quite chilly. Here is the ocean current diagram I was mentioning. All right, so in general, just think about this. And it really doesn't matter if we're looking in the southern hemisphere or the northern hemisphere. Colder currents tend to exist in the middle latitudes off of the west coast of continents. Okay, so in our example here, we have the California current off the coast of California, and then off the coast of South America, we have the Peruvian current, okay, which is also a colder current. By the way, any arrow that's blue is a cold current. Any arrow that's red is a warm current. Any arrow that's black is kind of like the connecting current, ocean current that connects the warm currents to the warm currents, the cold currents to the cold currents. All right, so look at the east coast of the U.S. now. The Gulf Stream current is generally going to run parallel to the east coast, and it's red, right? So that's a warm ocean current. Meanwhile, off the coast of, what are we talking about, Morocco here, northwestern Africa, we have the colder Canary current, which again is off the west coast of a continent. If we look down here in South America, we have off the west coast here of southern Africa, we have the Benguela current, which is a cold current. And then look at over here on the east coast of Africa, we have the Agulhas, this warmer current called the Agulhas current. And then over here up Australia, let's keep going here. The west coast of Australia, we have a cold current, which is the West Australian current. And then on the east coast of Australia, we have a warm current known as the East Australian current. And then going back to the northern hemisphere, very similar to the Gulf Stream current off the east coast of the U.S., we have the Kuroshio current. It's a warm ocean current just off the coast of Japan there. A lot of the typhoons and tropical cyclones that form generally tend to curve right along this warmer ocean current around that subtropical high pressure system. And then the colder current there in the northwest Pacific is the Oyasho. So as you can see, we got off the east coast the Labrador current, the Gulf Stream current, and it's generally the same no matter northern or southern hemisphere. Off the west coast of continents in the middle latitudes, you have cold currents, and off the east coast of continents in the mid latitudes, you have warm ocean currents. And this impacts our temperatures overall. Again, in the mid latitudes, just think about this. We have a westerly wind component prevailing or predominant, and that results in when the wind blows over this colder California current, now you understand why it's chilly in California in the summer. And then, for example, if you get a wind coming in off the Gulf Stream from the southeast to the east coast and the southeast coast in the summer, it's extremely hot. There's a major difference in the weather in San Diego. Draw that line straight across the latitude line to Jacksonville, Florida. There's a major difference in temperature, and it's due to these ocean currents and how the wind is blowing onshore from these various currents. All right, lastly, I want to talk about elevation. Air temperature normally will drop or decrease with height. Thus, a city near sea level would be much warmer, let's say, than a city at a very high elevation at the same latitude. So let's use an example. We have Denver, Colorado. Let's say the high temperature is 76 degrees Fahrenheit, and St. Louis is along the same latitude line. But it's actually 5 degrees warmer at 81 degrees Fahrenheit on the same day. The same air mass, again, along the same latitude line. The big difference here, why it's cooler in Denver, is because Denver is a mile high above sea level. So it's a mile up in altitude as compared to St. Louis, which is at sea level itself. So cooler temperatures, the higher elevations. This is the example I'm showing you. All right, that wraps up my little training video. We talked about temperature controls. They're very important. Anything from this latitude, where are you at in relation to, the sun and the earth relationship, how the tilt of the earth at 23.5 degrees on its axis, how much sunlight is striking various latitudes based on that tilt as the earth is revolving around the sun. The most intense solar radiation, remember, is at the equator. The least intense radiation is over the polar areas. And that helps explain, how the energy is dispersed or spread out. And then we again talked about land-water distribution, how land and water heat differently and cool differently. And then we talked about ocean currents, and we talked about all these various ocean currents around the globe. And then finally we ended our discussion on temperature controls with elevation. All right, that wraps up my video on temperature controls. I hope you certainly enjoyed it. And I've got some more videos to come, so stay tuned to the Spot on Weather YouTube channel for more. All right, that's all I got for now. Take care and God bless everyone.